here's a cartoon that will help you do this, and you can go to these PhET simulations yourself, okay? And they work really nicely. So here we go. We're gonna go over here, rub the balloon on this sweater. Now notice the protons don't come off, but the whoops, having trouble. All right, but the electrons do. The electrons and they kind of form on the outside of the balloon. Now watch what happens. Ooh, watch those electrons over here on the wall. Whoa, they're moving. In other words, those atoms are flipping along the wall there, and then I can stick it. Okay. Now actually, these electrons should have moved probably uniformly over the balloon if we gave them enough time. In fact, let's watch good old John Travolta here. Um, let's see, light ready. Hopefully they still have good old John Travolta. I mean, this is a standard that I show every year. PhET simulations, and so here we go. Now, here's what happens on a hot wintry day, especially like today, because today I'm talking to you on what is it? January? What the hell's the date? 16th, January 16th. It's Tuesday. This morning it was about 19 below zero, wind chill. So that means our heaters are blowing in our house, and it's really dry. And so when it's really dry in the house, that means there's not a lot of moisture for all these electrons in the air that are in the atmosphere to cling to and be neutralized. All right. So you got all these electrons just kind of floating around there, getting in the dust on the carpet. So when he kicks on the dust on the carpet, now watch what happens to these electrons. They're going to start forming slowly. It's going to take them a while, but they're going to form. Notice how they're spreading out the best they can. Okay, well, let's kick up some more electrons. All right, so there we've kicked up some more electrons. And now this is a conductor here. Okay, and a lot of times, if you develop enough charge, you can get your finger close enough that it will actually arc over. It will jump over through the air and charge. And I think that's what we're going to get here. There we go. All right, so that's pretty much charging. Okay, there you are. All right, so let's go back to the slides here. So that's by charging. Now we're going to end today with Coulomb's law. All right, Coulomb's law. Now notice, like forces attract each other. Here's a positive charge, or like charges repel each other. Here's two positive charges repelling each other, and here is two like charges attracting each other. F1 is equal to F2. Okay, and the formula for that is Coulomb's law. The magnitude of the electrostatic force exerted by one point charge on another point charge. Point charge means they're not moving. Okay, and basically we're setting up a theoretical world here. This is not the real world yet. The charges and electrons are oozing around all the time, but this gives us a framework to work with. Okay, and we can approximate what's going on with what's going on. Now, here is look at this equation. Have you seen this before? Sure you have. It looks exactly like Newton's equation for gravity, just different things. But it's a force. It's an inverse square law of a force. An amazing thing. Pretty cool. Okay, and it's Coulomb's law, and it's not that hard. Here is this echo knot. This is what we call the permittivity of free space, and it's 8.85 times 10 to the negative 12 Coulomb squared per Newton meter squared. Okay, and then we multiply that by 4 pi and take the inverse of it to get what we call the electric constant. So let me show you in the notes here. Echo knot. This is the way I'll write it. Echo knot. This is known as permittivity of free space. That's just what it's called. You know, don't ask me what permittivity means, why they call it that. That's like asking me, why do we call that a rhino? Hell, I don't know. We just call it the permittivity of free space. Okay? And it's equal to 8.85 times 10 to the negative 12 coulombs Newton squared per meter squared. Okay? And then when I multiply this by 4 pi, so I take 4 pi, echo not, flip it, this gives me k. And k is equal to 8.99, or 9.0 if you want, times 10 to the 9th newtons per meter squared per coulomb squared. This is a heck of a lot like big G, which is equal to, I forgot. Ha! I'm having a moment here. I can't believe I'm doing this. I really can't. 6.67 times 10 to the negative 11? Yeah, here we go. 6.67 times 10 to the negative 11 newtons per meter squared per kilogram squared. Okay. As a matter of fact, the kilogram and the coulomb are related. This is big G from when F is equal to G times M1 times M2, or mass of the Earth is what we use a lot of time, over R squared. This is the Coulomb's law. This is Coulomb's law. I can't believe I had to. Oh, first day of the semester is equal to K times Q1, Q2 over R squared. Okay, and we're gonna do a problem here, and I'll show you how to do them, and then that'll be enough for this.